Hello, my name is John Lee, and I'm the president of Alpha Training and Consulting. And I have a true passion for preparing students for ASQ certification exams. I've been doing it for over 20 years, and I just love it. But today, we're going to go over practice exam questions for the ASQ CQI exam. And we get those questions out of the CQI primer, which comes from the Quality Council of Indiana. What a great group of people they are, wonderful people to work with, and they have given us permission to use these questions. By the way, we use their primer in our online class. What we do is we have you listen to all our lectures, take our exams, and at the end you review the primer and we go over all the questions at the end of each chapter. It really helps students prepare for the ASQ certification exam. Now, if you're interested in that class, just go to www.asqcqi.com. Again, that's asqcqi.com, and it will tell you all about the ASQ CQI certification exam. It answers all your questions that you may have. Many videos posted on that website, so be sure and check it out if you have the opportunity. Now, let's get started on these exam questions. I think this is a hard one. They do these sometimes. A tank can be filled by 3 pipes separately in 20, 30, and 60 minutes respectively. In how many minutes can it be filled by 3 pipes working together? Okay, so what I'm going to do is I'm going to say, okay, how many times can you fill the tank up if you have 1 hour or 60 minutes? Of course, this one will be 1 fill in 60 minutes. But let's write this down. So return to your book again, because I'm going to be pulling this off and solving this problem. So one was 60 minutes. So I'm going to say, how many times can you fill this tank in 60 minutes? So 60 minutes goes in the numerator, and that 1 I could do in 60 minutes. So that's going to equal 1 fill. So remember, one of them could fill the tank in 60 minutes. Is that what it said? Can be filled by 3 pipes separately in 20, 30, and 60 minutes. Yeah. So one could fill 60 minutes so I'm just doing it mathematically. Okay, I'm giving you 60 minutes. It takes 60 minutes to fill it, creates 1 fill. That one's obvious, but now I'm going to do the other ones. So 60 minutes, I'm going to give myself how many times can it fill it in an hour. I'm going to keep the same units of minutes. And the other one was, where are we at? 30 minutes. 30 minutes what? Per fill. And so you go 60 divided by 30 is 2. So this one can be fill it twice. Fill it twice. And the other one was 20 minutes, so we have 60 minutes. And I can fill it in 20 minutes, so that hose is pretty fast. And 20 divided by 60 is 3, so I can fill that with that hose. I can fill it 3 times, 3 fills. Then we add these up, 1 filled, 2 filled, 3 filled. So 6 fills. So in an hour, we can fill it 6 times. So in 60 minutes, we can fill it 6 times, 6 fills. Then you do the math on that, and I'm going to have to draw my equal sign down here, by the way, because I ran out of room. So 60 divided by 6 is 10. And this is fills per minute, so it ends up being 10 minutes per fill. Yeah, 10 minutes per fill. 10 minutes per fill. That's not going to be easy for you. Many of you are going to say, well, why did you pick 60 minutes? Because I had one, and so that was 60 minutes, so I wanted to make this equal to 1 fill. So that's why I said 60 minutes here. Then I left the 60 minutes in all the other ones. So in 60 minutes, you get 1 fill out of this one, 2 fills out of that one, 3 fills out of this one. You add them all up, and that creates 10 minutes per fill if you're using all 3 of them. So that one I know is hard, and I don't know what to tell you other than you may not get 100% on all these, and but the main thing I think is don't give up. Just because you can't get 100%, if you could do all of these, but let's say 2 of these I think were kind of pretty hard, then let's say you could do all but 2 of these. That's 6 out of 8. That's 75%. If you can get 75% out of section 2, do a little bit better on the other sections, which I believe you can, you're going to be all right. So there it is, 10 minutes, 2.8 is D, and sure enough, 2.8 is D. All right, now let's start on question 19. This is, I think, a rather difficult one, so hang in there with me as we go over this. A covered above-ground cylindrical oil tank is to be painted white on the top and sides. The tank is 20 meters in diameter and 10 meters high. If 2 painters can paint 25 feet each in 5 minutes, how long will the job take? And notice the answer is in hours. So the first thing we need to do is take 2 painters. How many can 2 painters paint in meters per hour? Meters per hour. So we have some unit conversions to do here. And so let's do that one first. Then all we need to do is calculate the area of the sides of the cylinder and the top. And once we add those together, we'll just multiply that times the square meters per hour, and that will give us hours, and we should be able to solve this from there. So let's get started. Again, we're going to start by taking 2 painters, 25 square feet in 5 minutes, and convert that to how much can they paint in square meters per hour. So let's go ahead and do that. We'll get started doing that first. So here we go again. We're going to go, let me make sure I get up there, 2 painters. I'm just going to do a P there to remind you of painters since I lack room. And then 25 square feet per painter. 25 square feet. And that is per painter. And that is per 5 minutes, I believe. Yes, it was 5 minutes in the questions. 5 minutes. Okay, then I need to convert that to hours. So I'm going to convert this 60 minutes to hours. Just to convert it to hours. Then I'll worry about converting square feet to square meters here in a little bit. But let's do this much first. First, let's see if the units work out. And this painter, I'm going to make it the same symbol as the other one. So P stands for painter, and that's per painter. So these are going to cancel out. That painter is going to cancel out. And then these minutes will cancel out. Okay. And that will be square feet per hour. Square feet per hour will be what's left over. So let's get our calculator out. Remember, you always do math on 2 things, on numbers and with units. We always make sure our units come out to what we want it to be, and we do want it square feet per hour. Then we'll convert square feet per hour to square meters per hour later. So let's do the math here so we can make some room on our screen. So 2 times 25. So now I'm doing the math for the numbers. So 2 times 25 is 50, divided by 5, the 5 minutes, equals 10, times 60 equals 600. So the answer is ultimately going to come down to this, 600 square feet per hour. Now I'm going to convert that to square meters per hour. And I've already looked it up, so you'll need to look this up, but I already have, so I didn't have to take up so much time. And the conversion factor is 0.0929 square meters per foot squared. So of course the foot squared is going to cancel out, and I'm going to end up with square meters per hour. Now let's do the math on the numbers. It's going to be 600 times 0.0923 equals, and that is 55.38. I believe that's 0929. Yeah, that should be right. Let me check it one more time. 600 feet times 0.0929 equals 55.74. 55.74. So that's what I was looking for. Now I have 55.74 square meters per hour. And now I'll be able to use that to solve this problem. So let me write that down for you. 55.74 square meters per hour. And there we have it. 55.74 square meters per hour. And where did we get that? We got that from the information originally given to us in Factor. Remember, you do math with two things. You do it with the units first, then the numbers. That's a very important skill set to gain if you're going to pass this test. Now we still have some more unit conversions to go, because now we need to calculate the area of the tank. The area on the tank. So you need to go to your primer, which I'm going to do right now, and go to Chapter 2. I should have had these pages out already, but there's some pages, if you'll recall, in there that will help you calculate volumes. And I just found it, volume calculations. On the revision I'm working on, it's page 22, and I just want the lateral areas as 2 pi RH. Area of sides, the area of the sides. Area of the side equals 2 pi radius times height. And I just barely had enough room on there for that. So that's of the side. Then I need to also get one of the top area of a circle. And the area of the top, I'll just put top there so we'll remember, is going to be pi r squared. All right. So there we go. There we have it. We have everything we need here. There's our unit conversion. There's the area for the side, 2 pi r times the height, and the top is pi r squared. So let's begin our calculation of the areas. And the tank is 20 meters in diameter. Okay. And so let's do the area of the side first. Area of the side equals 2 times pi times the radius. Now they said 20 meters diameter. Don't get tricked on that. So that's 10 meters radius. 10 meters radius times the height, which I think is 10 meters also. 10 meters high, that's correct. So this is going to be meters and 10 meters high. And let's do the math on the units. It's going to be square meters. Well, for an area, you want it to be square meters. So now we just need to do the math here to get the area of the side. So this isn't going to be too hard. So there's the calculator. I'm going to go 2 times, and I'm going to hit pi. Pi is right there. You don't have to do it in individually. 2 times pi, and then I'm going to go equals times 10 equals times 10 equals, and that gives me, I'm going to pull it up so I can see it better, 628.3, let me see, 32. It's 628.32 meters squared. And I don't know if I had enough room for all of that, but I got the number on there. The meters didn't quite make it. It's right there. So this is 628.32 square meters. And that is just the sides of the cylinder. This is just calculating the area of this side of the side of the cylinder. So now we need to calculate the top, which is pi r squared. That will give us the area of the top. So that'll be pretty easy. Area of the top equals pi times 10 squared. Okay, so let's do that. Get my calculator out here, and I'm going to go pi times radius is 10, and I'm going to hit squared. See that squared button right there? Squared. And I'm going to go equals, and that's going to give me 314.16. 314.16 square meters. So now I just need to add these two together, and that will give me my total area. So I'm going to left that in my calculator. I'm just going to go plus 628.32 equals, and the total area is going to be 942.47, it's actually 0.48 meters squared. Now I'm going to erase all this so I just have this left over. So again, how did I get this number? I calculated the area of a side, calculated the area of the top, added them together. Now I'm going to give myself some room and erase all this and put the area of that cylinder up here and the top. 942.48 square meters. All right. Now that I have that, what I have to do is I want to know how many hours. So I'm going to leave this in the numerator, and I'm going to put this in the denominator. Now the meters will cancel, and when you have a number like this, meters per hour, it's invert and multiply, so hours will actually end up here. Those are the units I want. So now let's go back here, and I left my 942.48 area in there. Now I just need to divide by 55.74. That will give me 16.908 hours, 16.91 hours. And that is hopefully, after all that work, is hopefully the answer. So let's go back here, and we can round that up to 17 hours. I just looked down and saw that's what they did. And so the correct answer, let me get it up here and focus it. So the correct answer, hopefully, is B, 17 hours. So 219 is B, which is 17 hours. Okay, let's go ahead. 221, from a piece of sheet metal 12 by 24, how many 2 by 2 pieces can be sheared? Well, this one isn't too difficult. Notice it didn't give us any units or anything. It doesn't matter. So we'll multiply 12 by 24, and that'll give us the area of the big sheet. And then we'll go 2 by 2, which will be 4, an area of 4 square units. And we'll see how many 4 fits into that area, and that will give us how many pieces can be sheared. So let's do that. So here are the numbers. Let me see. There it is. 12 by 24. Equals Let's get out the trusty calculator. 12 times 24 equals 288. There we go. 288 square units. So I put a square there to remind you they're square units. They didn't give us what square units. It doesn't matter. They're all the same units. So we don't need to do any unit conversion. Now let's do the other one. Was 2 by 2 equals 4 square units. Now that we have that, we just simply take this larger sheet, which is 288 square units. We don't know, it may be square inches, maybe square yard, doesn't matter. And we want to know how many of these 4 ones will fit in there. 4 square units. And to do that, we simply go 288 divided by 4, and let's see what that equals. So there, I left the 288 in there, divided by 4 equals. That equals 72. So it's going to equal, we're going to be able to cut out 72 pieces. 72 pieces, and that was the question. So let's go back. 21 is 72, which is A. Let me see if that's the case. 221 is A, so we got that correct. Which of the following would be an appropriate expression of 71,000 in scientific notation? Well, it should be, usually they do a whole number like 7.1. That's usually how you do it correctly. So it would be 7.1 times 10 to the 4th. But notice they don't have 10 to the 4th here, so we know these are incorrect. Problem is, so are these. Because these are engineering notation, not scientific notation. So this question is kind of messed up, to be honest with you. But the correct answer will be 7.1 e to the 4th. Remember, e takes the place of times 10, so it's really 7.1 times 10 to the 4th. And so it's kind of messed up, but that is the correct answer. All measurements require which of the following? All measurements, that's key word, all. A definable standard that is internationally accepted? Yeah? No? Yeah? Well, the only thing I like this one, except it has to be internationally accepted. It doesn't necessarily have to be internationally accepted. Sometimes you create your own measurement system. You have to create your own procedure for calibration, etc. But that's not bad. We'll see what the other ones are. Automatic calibration? No, not all. A physical reference? No, not everything is a physical reference. In fact, most are not. Most standards are experiments created in a lab, such as length is wavelength of light. I think the mass is the only one that has a physical reference. So a person to operate the equipment? No, there's automated equipment. So in other words, they're all wrong, okay? And sometimes you run into those, but the one here that is better than the other ones, in my opinion, is A definable standard that is internationally accepted. The internationally accepted bit I'm a little uncomfortable with, but it's much better than the other ones. Has to be A. 3.4, are you A? Yes, it is. The weight of an object is dependent on the location of the object? Yes. In my engineering school, they always said gravity was a constant, but on the surface of the Earth it is not. Probably I'm not sure why. Part of it could be the mass below you, I suspect. And so it is dependent on the location. So if you ever want to feel good about a diet, go weigh yourself at a place with a larger gravitational pull, and then just go measure yourself later at a lower gravitational pull, and you'll lose weight. The problem is it doesn't make that big of a difference. So weighing your body weight isn't going to make you feel that good about yourself, to be honest with you. However, for real sensitive measurements, it can be important. And so A is true, equal to the object's resistance to acceleration. It's not equal. Force equals mass times acceleration, and it's mass, not weight. Two different things. Weight is dependent upon gravity, mass is not. Your mass is the same on the moon as it is on the earth, as it is on Jupiter, but weight changes with gravitation. So A is correct, B is not. An increasing function as the altitude increases. No, weight doesn't increase with altitude. If anything, it will decrease. Proportional to the number of atoms in a mole. No, that may have something to do with mass. But anyway, it's A, dependent on the location of the object. 3.8, lay it on me. Yes, right again. 4.8, the standard deviation refers to which of the following terms for a typical set of measurements. The standard deviation. It's not accuracy. Accuracy refers to bias. Remember that. They're going to test you on that. High accuracy means low bias. That always shows up on the test. Error. There are error terms that have to do with sigma, but in this case it's not. Because I see the other two down here, and it's going to be one of those. Precision. Precision is sigma of the measuring instrument. So that could be it. Uncertainty is sigma of everything of importance in measurement. So uncertainty, the standard deviation refers to which of the following terms for a typical set of measurements. So that's only part of it. This is all of it, uncertainty. 4.8 is going to be D. 4.8 is D, and that is correct. I'm going to go back to the whiteboard, and we're going to play around a little bit here. Make sure you understand this. Let me clean it up for you. And let's get it out where I can write on it. Okay. This is uncertainty. First of all, sigma total. Let's do that. Sigma total equals, in measurement, sigma of the equipment squared plus sigma of the operator to operator squared plus sigma due to change in temperature plus sigma due to change in humidity plus, oh, you have to square all those. Remember, this is how you add sigmas together. You square them, add them together, and take the square root to get sigma total. This is called uncertainty. That sigma total in measurement is called uncertainty. Uncertainty. I don't have enough room to write it, so I'll just call it uncertainty. But it has anything that's important, standard deviation that's important that impacts measurement in a negative way is assumed to be part of uncertainty. And so it's pretty big. There's precision. Sigma of equipment, of course, is precision. And there's also sigma of the standard you could put in there. There's all kinds of sigmas you could put in there. But that's called uncertainty. So hopefully that helped you. Today we're going over Chapter 5 of your CQI primer. And these are the pages I bring with me. These are out of the critical stack. But they always like to, on the test, ask questions about screw threads. So I have that one. And it also gives the nomenclature for threads right here. That's a very important one. And then, of course, I have the table for the symbols in GD&T. And those ones you'll always need on the test. Those should be in your critical stack. All right, let's get started here. There's only 28 on this one, which means I'll do 14 of them, at least on the revision I'm working from. The distance from a point on a screw thread to a corresponding point on the next thread measured parallel to the axis is called. So we come over here to this drawing. Since I have it out, I'll show you. And there is the distance from one thread to another, measured parallel to the axis. It's called pitch. Pitch. If it's the root there, I guess you call it, I'm not sure what they're measuring there for width. I could read down there, but the answer to this question is definitely pitch. And yeah, there it is. Thread pitch B, 5.1 is B. Let me turn this over where I can see the right chapter here. And that is true. B is correct. Related to geometric tolerancing, this is GD&T, the supporting datum plane that must be contacted at the three highest points on the surface is the primary datum. It's going to be A. So remember this, primary datum must have 3 points of contact, 3 points define a plane so you can set it down stable. 2 points is the secondary datum, it keeps it from rotating, and 1 point keeps it from moving up. And those are primary 3 points, secondary 2 points, tertiary 1 point. And so this has 3 points, going to be primary datum. 5.2 is A, that is correct. The probability of rejecting material produced at a rejectable quality level is defined as, I already know it's 1 minus beta, because you rejected it and it was a poor quality level, so you were supposed to reject it, so you made the right decision. Whenever you make the right decision, it's going to be 1 minus something. And when it's should be rejected and you reject it, it's 1 minus beta. When it's good and you accept it, it's 1 minus alpha. But I'm going to show you on this table. This table is very important for this part of the test. And it's in your chapter 6 there. And so you can look it up from your primer. But here it is, lot quality. In reality, it's bad. And that's what the question said, it was bad. And you called it bad. And that's 1 minus beta, or consumer's confidence. Okay, sometimes they also call it the power of the test. Okay, and so we'll just review all of this right now. If in reality the lot's bad, you accepted it, that's called beta risk, also referred to as type 2 error. If you called it good and it is good, that's 1 minus alpha, producer's confidence. If you called it bad and it's really good, that's alpha risk, also known as type 1 error or producer's risk. Beta is also called consumer's risk. And they'll use that on the test, so be aware of that. So very important matrix. I'm sure that one's in your critical stack. And you need to have that available when you take the test. Very, very important. So from that one, I already know it's 1 minus beta. And that is D. 6.4 is D, no doubt. Yes, it is. Using ANSI ASQ Z1.4, the AQL is always determined at what probability of acceptance on the OC curve. So I'm going to take this opportunity to show you the OC curve, and I'll just draw one. Okay. All right, there we go. It'll work. So you have 2 axes that we're interested in here, and this is the y-axis is the probability of acceptance. Probability of acceptance. There we go. And this is the percent defective, percent bad parts in the lot. So this represents reality here, that percent bad parts. So you're all knowing somehow, and you look at a lot and you say, oh, that has 5% bad parts in it. And it is 5%. So this is reality, percent bad parts. Now, this is your probability of acceptance. Obviously, you want to accept it if it's within your AQL. So if your AQL was right here, you would want to have a high probability of acceptance from here over. And the perfect OC curve looks like this. I don't know if I drew that perfectly, but this is 100%. That means your probability of acceptance is 100% all the way along here until you get to your acceptable quality level. After that, you don't want to accept it. The risk goes to 0%. So that's exactly what you'd like, isn't it? But it's not the way reality is. That is not the shape of an AQL curve. An AQL curve is actually a binomial distribution. And you should remember that, by the way. I'll write it down here. There's 2 possibilities. It's most likely binomial, but it could be hypergeometric. Hypergeometric. So there should be an R in there. Hypergeometric. And that won't fit on the screen, but oh, it did. So those are the 2 curves, but it's most likely binomial. But it's going to be binomial or hypergeometric. That shows up on the test quite a bit, so keep that in mind. And so what this tells us, if this is my AQL, and I'm just barely on the AQL, or let's say just barely past the AQL, and let's say that's 5%, then that means I wanted to reject it, but there's still a 5% chance, probability that I will accept it. So this is probability of acceptance. This is percent bad parts, and of course your AQL fits in there somewhere depending on what your AQL is. Okay, I think usually this, I'd say on average you're right around high 80, 90% that you will make the right decision. So they're not perfect. These sampling plans are not perfect, but they're used all the time, and it's better than doing nothing. Of course, you're better off improving the process. ASQ doesn't really have this great love affair with inspection. They would rather have you improve the process till inspection isn't necessary. And they'd rather have you inspect during the process so you could see if something was going out. And so just keep that in mind. Those things show up on the test. Now, I'm going to go back here and read this. Well, I just will put it back, and if I need to, I'll refer back to that chart. So using ANSI ASQ Z1.4, the AQL is always determined at what PA, probability of acceptance, on the OC curve. Okay, first of all, there isn't a constant probability of acceptance. It changes depending upon, for example, the risk level. Do you want level 1, level 2, level 3, etc.? So that probability acceptance is going to change with the plan. So to give any constant number here is not right. So it's going to be none of the above because it depends on the sampling plan. Remember those S levels, and then you had level 1, 2, and 3. They will all have a different probability of acceptance. So it's going to be D, none of the above. 6.6 is D. And it is D. Question 1, what is brittleness? Now, I can already tell you a lot. In this chapter, a lot of them are lookup, and as you know, I don't do a lot of lookup. However, I did take out a couple of pages, the ones that are in your critical stack, to help me get through this section. But I know most of it pretty well, so I won't have to look up too many of them. But what is brittleness? That's in your book. It's under the, there's a bunch of vocabulary tables in there. You can find that. But brittleness is, you know, if you drop something and it just disperses all over and breaks into little pieces like glass, that is brittleness. And so let's see what the potential answers are. The tendency to deform little before fracturing. In other words, it doesn't bend much before it just shatters. And that is the correct answer, A. The ability to withstand repeated loading, no, that's fatigue strength there. So you may want to make a note of that, or it's in your book also, so you can just look those up. The ability to resist shock, that's impact. And the yield strength of a material is exactly what it says it is. It's about yield strength. But A is the correct answer for this one. Let me look that up. 7.1 is A. That is correct. So we're off to a good start here. Plasticity is the ability of a material to. It's like plastic. You can kind of pull it around. It doesn't break. That's plasticity. Resist a sliding pass type motion. No, that's shear strength. Shear strength. Withstand erosion by friction. That's erosion resistance, I think. So that's not plasticity. Undergo permanent deformation prior to breaking. Yes, that's plasticity. So it's kind of the opposite of brittleness. If you pull on a part and it's brittle, it'll, you know, it could shatter. But if it has plasticity, you stretch it, and it'll keep stretching a long ways before it breaks. But even though it will stretch, if you let go, it may be permanently deformed. That's the plasticity range. So that's going to be it. Undergo permanent deformation prior to breaking. That's plasticity. Demonstrate good compressive resistance. No, that's compression strength. And so 7.2 is no doubt C, and it is. 10, for the normal probability distribution. Whenever you see the non-normal probability distribution, guess what they're talking about? The z-table. The z-table. So you'll have to take this out and use that oftentimes. But let's not, we're ahead of ourselves. Let's see what the question says. By the way, we're going to do 20 out of this section because there's only 40 in this. And I always do half unless it's greater than 50, then I do 25. For a normal probability distribution, the relationships among the mean, median, or the median, mean, and mode are that on a normal distribution they are all equal. They are all equal. And there it is. They are all equal to the same value. A is going to be the correct one. The mean, mode have the same value, but the median, no. It's A. I already know it's A, so I'm not even going to read the other ones. A. What value of Z in the normal tables has 5% of the area under the tail beyond it? Okay. So this is Z-table problem. It even says Z-table right there. What value of Z in the normal tables has 5% of the area? So you have to use this in reverse order. What it says is 5% of the area. So you see the bottom of the normal distribution up there. These numbers are that area under the curve beyond that many sigmas. And it says it wants 5%, so we have to do it in reverse. So I bolded this center line, I always do, and I'm going to drop down here until I find 5%. 5% is what? 5 divided by 100. 5 divided by 100 equals 0.05. So I'm looking for 0.05 in the main body. Once I find the number, I can go out and see how many sigmas away it is. But right now I need to find 0.005. Well, I'm getting fairly close here. Look at that, 0.007, 0.00539. So that's pretty good. Then I'm going to find something even closer, and I have to go this way. Look at that, 0.00508. So that's, oh, I'm doing 0.05. I'm making a mistake. I'm looking for 0.05. Okay, come on, John, you can do better than this. So 0.05 is really what I'm looking for, and there it is. Look at that, 0.0495, and so that's not exactly 5%, but this is 0.0, so it's somewhere between these two. In fact, 5% is directly in between these two. So let's go across. It's going to be 1.6, and it's going to be between 4 and 5. 4 and 5, right in the middle of 4 and 5. So the answer is going to be 1.645. See if that, you may have to watch me do that a couple times. That's why we put it on video, so you can do that. But the answer is definitely going to be 1.645. So 814 is B. 814 is B. That is correct. All right, let's get started on question 22. Which of the following statements is most applicable to the three curves below? Well, number 1 is a normal distribution. Number 2 is a right skewed distribution. Number 3 is a left skewed distribution. Now, if that doesn't sound familiar, you may want to go back and take that non-normal distributions module again. Towards the end of it, we go over all these different distributions, skewed to the right, skewed to the left, etc. Curve 2 is skewed to the left. No, curve 2 is skewed to the right. Remember the whale tail? It's always in the direction of the tail. So this is right skewed, not left. So A is incorrect. The mode, median, and average are all the same on curves 2 and 3? No. As you'll recall, the mode is the longest line here, and then it always goes towards the tail, and median is always in the middle. So in this curve, right skewed, the mean will be less than the median will be less than the mode. And of course on 3, that will be the mode, the longest line, they'll go this way. So mode will be greater than the median will be greater than the mean. Again, if you don't remember that, you'll need to go back and listen to that non-normal distributions module, and that part is towards the end, by the way. Okay, curve 3, there it is. Curve 3 indicates an out-of-control condition. Not necessarily, it may be predictable. So it does look predictable to me. It's just skewed to the left for some reason. Curve 1 represents good control. And that's true. Remember, the poster child of predictability is the normal distribution. What does predictable mean? It means it's in control. So this one, 822, has to be D. 9.1, let's get started. Which of the following actions or techniques is most useful in determining the original fundamental cause of a product or process nonconformance? Fundamental cause sounds like the root cause, doesn't it? That's a key word for this one, I think. They're trying to find root cause. Is it continuous improvement? Well, it could most certainly be part of continuous improvement, so it could be correct. Pareto analysis, no, it doesn't have any of those priority or any of those key words for Pareto. That's not the case, but there's the one we knew was correct in the first place. Root cause analysis, that fundamental cause is root cause. And prevention action, not necessarily on this one. So it's going to be C. 9.1 is C, and that is correct. It's great to start out on the right foot here. Let's do number 2, audit. Oh, by the way, we'll do 20 on this one. There's a total of 40 here, so we'll do half of them and leave the other half for you. Audit follow-up is typically conducted to close the corrective action loop. That is very true. To surprise the auditee, no, we don't surprise in auditing. In quality auditing, we don't do surprise audits. So that has to be incorrect. To catch any deficiencies missed on the first audit, that is not the purpose for audit follow-up. A is definitely the better answer. To demonstrate the authority of the auditing organization. Oh yeah, you're going to go out there and show how tough you are. Hopefully that's not what auditors do. I'm sure there's some out there, but that's not the correct way to present yourself, obviously. So 9.2, audit follow-up is typically conducted to close the corrective action loop. 9.2 is definitely A. Let's go look, and it is A. Congratulations, you have almost completed that video. I hope you've learned something new that will help you with your certification exam. Remember, if you have any questions concerning certification exams, as you can see, I've passed most of them, just contact me through my website at alphatc.com. Go to the Contact Us option and send me a message. I'll get back to you as soon as possible. Hey, thank you, and have a great day. Goodbye.